external speaker. Dr. Mario Sznaier. Mario is a Dennis Picard Chair Professor at the Electrical and Computer Engineering Department at Northeastern. Prior to that, he was at Penn State, and he also had visiting positions at Caltech. I keep reading this biography.
I mean, it depends. You want me to banish it?
And he happens to be my PhD advisor as well, so as a side topic. And with that.
All right, thanks, Nechmie. So, very happy to be here. Thanks, Nechmie. She was been treating me like royalty. Nice, really nice dinner yesterday. And then she made me work really hard. She has me tightly scheduled, like in 15 minutes thing. So I'm talking to people and I'm having fun and said, okay, time to talk. Anyway, so what I want to do today is give some observations about what makes control problems hard or easy. And of course, I picked the title to be provocative because we all know that if a problem is convex, it's easy, it's not convex, it's hard. I mean, you go and talk to Pete here and he will tell you about IQCs and how we do convex optimization. And my point is that maybe things are not that simple. Okay, so here's the bad news. I mean, if you're a student doing control, don't look at this. But the bad news is that control, and certainly linear control, is considered to be a solved problem, right? So if you go to your department head and you say, look, let me hire a control guy, this guy is outstanding, I say, no. I mean, that's a solved problem. Why should we work on a solved problem, right? And I mean, it's our fault. We worked really hard during the past 20 years to essentially work ourselves out of a job. And again, Peter in here, it's partially to blame because, I mean, we are at the point where you have your performance specs, you have your data, you turn the crank, and magically, without looking inside what's inside that box, a semi-definite program or a bunch of linear matrix inequalities come out. Then you crank the box again, and something called, let's say, interior point method, and you get two things. You get a controller, which is great, but more importantly, you get a certificate that your controller is going to work. Okay, and all of this is now knowing which amongst all the commands that Peter wrote, you need to invoke, right? So again, blame him. And we can deal with hundreds of parameters, okay? So again, depending on how you look at this, this is bad news because we don't have problems to work on. Good news because we can solve really hard problems, okay? And question is, can we scale? And this is motivated by a project I had with some folks from civil engineering, where we have a city, it's completely sensorized. Let's say a hurricane is coming. You want to position your assets so you can either minimize damage or you can recover right away, say put some generators, do things. And then, yes, you can write an SDP. And yes, you can use your tools. And good luck, because bam, you hit a wall. And the reason you hit a wall is that some of the methods that we have actually have very poor scaling properties. So you can work, say, hundreds, maybe thousands of parameters if you push it. Beyond that, MATLAB says, sorry, cannot help you, okay? So part of what this talk is all about is to try to understand why some of the problems we're trying to solve are actually hard problems. Where is this difficulty coming from? Okay, and also maybe we can actually go to our department here and say, hey, we need to do big data. Everyone needs to do big data. I have this candidate that's doing control and big data. Let's hire that person. Okay, so I mean, this is supposed to be a cartoon where you actually have lots and lots of data and you're trying to make a decision in there. Okay, so I'm envious of my machine learning colleagues, right? Because they can do big data. They're sitting in there saying, hey, come join me. Funding is great over here. We're having funds. We're having lots of papers. Look how happy they look, right? And me being a sort of an older control person said, I love to join you, but what am I exactly getting on? I mean, can you tell me what big data is? And they go, yeah, right. So what do you do when you don't know the answer to a question? I mean, you go to the source of all wisdom, right? AKA Wikipedia. So you ask Wikipedia, and Wikipedia tells you, this is what big data is. Whatever challenges your existing algorithms, right? So if you can solve it, it's not big data. If you barely can solve it, that's big data, right? And honestly, this is sort of the best definition I found of big data. Problem is that this tells you what big data is. It doesn't tell you what makes data big. So my next question is, what makes data big, right? And again, this looks like a trivial question. I mean, from the audience, what makes data big? Or it's 100 big, it's 1 terabyte big. What do you think? Honestly, I mean, this is a real honest question to the audience. It's 100 big data, 200,000. And the question is depends. Turns out that maybe big data is not really related to size. And again, that's in principle, when I go and say, look, you know what? In control, big data could be 100 or 1,000. Here's what I have this real inferiority complex. Because I talk to my colleagues that are doing machine learning and they can deal with Google size data sets and I can't, right? So is that because we as a control community are not smart enough, or is there something that makes our problems intrinsically hard? And I'm going to argue that there's something that makes our problems intrinsically hard and try to see what that something is. Okay, so that's why this hard or easy comes into play. So before I can actually figure out why sometimes big data and control is about 100, I want to see what makes a problem hard or a problem easy. And maybe the answer is convexity. We all, or at least academically, I grew up in the era of LMIs and semi-definite programs. We have this wonderful book by Stephen Boyd. So I think I can, or Peter can convince you that if a problem is convex, it should be easy, right? Maybe. Here's an example of a problem that's both convex and NP hard. I mean, if you try to do any optimization over copositive matrices, that's an NP hard problem. Okay? So just saying that something is convex, it's not enough. Now, you can say, look, you're cheating, because essentially, hidden in here, it's an infinite number of constraints. Because to check that a matrix is copositive, you have to check that X transpose AX, it's positive over all vectors with non-negative or positive entries, right? So what if we consider something that's a little bit more reasonable? So let me add that I want my problem to be convex, and I want it to be self-concordant. And if you're familiar with Boyd's book, you know what I'm talking about. But I mean, it's a condition about the growth of the third derivative and the second derivative. And what self-concordance buys you is that then we know that we can solve our optimization problem in a surprisingly low number of Newton iterations, right? So maybe an easy problem is a problem that's both convex and self-concordant. And here's an example. This is an actual rig that I was involved with. It's a cantilever beam that we were using for damage mitigating control. And the idea here is that that beam is extremely poorly damped, has a horrible resonance, and you go and you drill a hole. And as a control person, the task is get it to track a given trajectory, and you know what happens. You design your tracking controller. The moment you start tracking, you excite the resonance, and the thing breaks very quickly. So the idea of damage mitigating control would be design a controller that does the best tracking that you can, and at the same time, doesn't break the thing, right? And you can use this as a proxy for, say, you have some civil infrastructure that's been damaged, a bridge or something like that, and what you want is extend the life for as long as possible while you're fixing it, okay? Turns out that because this is very poorly damped and has a huge resonance, in order to design a controller, you need a really good model. And in order to capture that model, unfortunately, you need lots of data points. So if you're using control-oriented identification that reduces to a bunch of linear matrix inequalities or a semi-definite program, when you try, by the time you get 350 points, you're really challenging MATLAB. And by the time you go to 400 points, MATLAB says, sorry, cannot help you. Okay? So according to this, 400 points is actually big data for some classes of CSID. And we actually got frustrated with this, and we coded our own ADMM-based method. And at that point, we could push things to maybe 500 points if you're willing to wait for an hour, but we couldn't get beyond 1,000 points. Okay, so this is an example. I mean, I didn't tell you why, but at least it's an illustration that in control, hundreds points, 1,000 points could actually be big data for reasons yet to be determined. But empirically, if I have few hundred points, 1,000 points, I'm in trouble. Okay. So I don't really know what makes a problem easy. I mean, clearly, convexity alone is not the right answer. So maybe we can look at the other end. What makes a problem hard? I mean, the type of problems that you look at it and say, I'm not gonna do this, or you're going to give it to your smartest student and have her do that, okay? So obviously we know what a hard problem is. If your problem is non-convex, we've been trained to run away, right? Here's an example. This is as bad as it gets. I'm trying to optimize an indefinite quadratic form over the hypercube. So it has all the markings of a horrible problem. Binary variables, indefinite quadratic form. I can solve this in my Mac with 100,000 points in less than a minute. Okay, so clearly this convex versus non-convex dichotomy, it's not capturing what makes a problem hard or not. Okay, don't get me wrong. I mean, at the end of the day, I'm going to end up solving convex problems because that's all I know what to do. But I'm going to solve the right convex problems, and I'm going to use a lot of tricks to make sure that computational complexity doesn't kill me. Okay? So let me look into this a little bit more. How come this is something easy? How come the other problem was hard? And to do that, I'm going to look at QCQP, quadratically constrained quadratic programs. And those are a class of problems that are known to be generically NP hard if, I mean, you have to minimize a quadratic objective subject to quadratic constraints. If your constraints and objective are indefinite, you're in trouble. Okay? But in principle, we can try to write this in a form that looks like almost like a linear matrix inequality. I mean, you write it, or a semi-definite problem. You write it as minimize a trace of something subject to constraints written in the form of trace of something. And then, of course, the standard trick here is you take that outer product, you call that X. And then you write something that the last line there, it actually looks like an SAP. But we're leaving out something that's very important. What we're leaving out is that if we just replace, I mean, we just consider X to be only positive semi-definite, this is a super solution because the true X has to be rank 1 because it's the outer product, right, of that vector. So, of course, I can put that rank 1 condition back in, and I get a problem that's exactly as difficult to solve as the one I started from. So it doesn't make any sense. So the question here is there any way I can get that rank condition for free? And this is when things get interesting. This is some work related to some work that Javad Lavae from Berkeley did about 8 years ago. You start by making the connection between the optimization problem you're trying to solve and a graph called the correlative sparsity graph. Your graph has one node per each one of the variables in your optimization, and it has an edge if the product of your variables appears in your objective, or if the two variables appear in the same constraint. And what Javad showed is that if that graph happens to be a tree, then the semi-definite relaxation that I show you is actually exact, which means you can throw away that rank condition, you still recover that original solution. So that was an example. I mean, if your QCQP problem satisfies this property, that's an example of something that seemingly looks very hard, and actually it's an easy problem to solve. It gets even better because you can show if that correlative sparsity graph is a tree, then the second order comprogram relaxation is exact. And second order comprograms are easy to solve. And 2020 hindsight. This is how I crafted that problem with 100,000 variables that can solve in my Mac. I started backwards. I started, okay, let's have a tree. Let's create a problem that has that as a correlative sparsity graph. Easy. I mean, I can dazzle you, show, look, I can do nonlinear things in minutes in a Mac, but that's because the underlying problem is actually an easy problem, right? So the take-home message in here is not so much convex versus non-convex. You actually have to dig deeper, and you have to look at the structure that's underlying the problem they're trying to solve. And actually, sparsity helps you. I mean, if you have the right kind of sparsity. And of course, I mean, if you read that paper by Javad, there are other conditions. Say, for instance, your graph has to be weakly acyclic, blah, blah, blah. Then under certain conditions, the SAP relaxation is actually exact. So how can we use this? Or how can we use things like this to understand the complexity of the problems we're trying to solve? And what I'm going to talk about is a sort of related problem. It's the problem of matrix completions. So suppose that I give you a matrix. The things that are xij, those are fixed variables. The things that have question mark, those are things that you have to find. And I ask you, can you go ahead and find those question marks such that the completed matrix is positive semi-definite? And of course you can. I mean, one thing you can do is write 5 lines of CVX code, run it. If it's feasible, you're done. If it's unfeasible, the problem is not solvable. But what becomes interesting in here is that you can answer that question without actually doing any optimization. And the idea is, again, you look at the underlying graph. The graph has 1 node per row or column, and it has an edge if the variable xij is specified, and no edge if that's a free variable. So if you look at my example in there, you see x12 there's an edge between 1 and 2, because x12, it's a variable that's specified. There's no edge between 1 and 3, because x13, it's a free variable, okay? So, I mean, there's a tiny technical point here. I have to complete the graph to be chordal. But let's assume that the graph is chordal. That means that any cycle, has dimension 3. Then what you can show is that take your graph, chordal graph, do the decompositions in cliques. And if the graph is chordal, that's something that you can do in linear time. And then you look at the submatrices that are associated with each one of the cliques in the graph. So for instance, the yellow clique involves 1 to 5. So it's x12, x12, x22, x25. And there's something called Grun's theorem. And what Grun's theorem says, you can complete your matrix to be positive semi-definite if and only if, when you look at the submatrices related to each one of the cliques, those are positive definite. So you look at those, you can actually answer the question without having to do any computations other than the chordal decomposition of your, the composition of your graph into cliques. There's things even better. Suppose that I ask you to complete this matrix with a minimum rank completion. There's something called Dancy's theorem that says the minimum rank completion of this matrix is the maximum rank over the cliques. And you can find a completion that has that rank. Okay? So you can answer all sorts of interesting questions about matrix completion by looking at the associated graphs and the cliques. Okay? How's this? I mean, this is an interesting factoid. How's this going to help understanding what things make problems hard? And the idea is, suppose that I give you a semi-definite program in like a primal form. So you're trying to minimize the inner product or the trace of XA naught subject to constraints of the form trace XAI given, and X has to be positive semi-definite. So what you do is you do the correlative sparsity graph, and then you use that to decompose your SDP. So let me give you an example. The idea is, suppose that I have to, for whatever reason, I want to minimize X14 subject to that linear constraint that involves only some of the elements of my matrix. And of course, I want my big matrix X to be positive semi-definite. Okay? If you look at this, you'll notice that, for instance, the variable X43 doesn't appear neither in my objective nor in my constraints. So it's sort of a filler variable. The only role it plays is that you want it there to make sure that your matrix X becomes positive semi-definite, right? So in principle, I don't even need to find that. I only need to know that it exists. And what that allows me to do is start with the graph and divide your graph on clicks. And then when you do the optimization, instead of taking that matrix X and imposing that it's positive semi-definite, well, lots of extra variables, all I need to do is I need to impose that my matrix is positive semi-definite only over the clicks. Okay? So the bottom line is that computational complexity is related to the tree width. Computational complexity ends up being related to the size of the maximum click in your graph. Okay, now we're getting somewhere, because that means that if I have 1,000,000 points, but the clicks in the graph are small, that's an easy problem. If I have just few, say 100 points, but are tightly interrelated and the click happens to be size 100, I'm in trouble. Okay, so that actually explains why control problems are hard. Because typically, when we deal with control problems, we have temporal correlations. Everything is correlated to something else, so you end up with large clicks, and that's what kills you. And so this is an interesting connection that sort of explains what's going on. And just set aside a comment on how can you use this. It turns out that once you do the composition of your graph into clicks, you can do relaxations where instead of forcing your matrix to be positive semi-definite over a click, you can pick a different cone. You can say, I want, say, the diagonally dominant cone, or I want the SDD cone over that click, and that gives you different approaches. So here's an example where if you look at the gray area, I mean, that gray region is the actual feasible set of a semi-definite program. And what I have in different colors is once I do the click decomposition, instead of forcing each click to have a positive semi-definite matrix, some of the clicks I choose something else, like a different cone that has an easier representation. And so let's say that I'm trying to minimize that CX. So you see where the solution is going to be. If I choose the decomposition on the left, that's horrible. But if I choose the decomposition on the right, I can solve the problem with much lower computational complexity. So just to give you an example, we have a bunch of agents, and what we're trying to do here is we're trying to estimate the H infinity norm, meaning the L2 to L2 gain or disturbance attenuation. Of course, we know how to solve this. We just write the bounded real lemma. We have a huge matrix. Good luck. Because, I mean, we tried this, and MATLAB says, sorry, I cannot help you. Right? Then we turn around and said, you know what? We're going to use this chordal decomposition. We have one large click that it's all the agents that are in the head of that star that are connected. And then we have smaller clicks that have to do with the things in the arms. And to make things even easier, we said, this large click, instead of using something positive semi-definite, I'm going to use block factor with 2 matrices. And using that trick, we're able to actually get an upper bound on the H infinity norm in 1 minute. And then we turn around, we look at the KKT conditions, and we find out that actually that was the exact solution. Okay? Which means that we started out with a convex problem that was horrible to solve. We couldn't solve it. We did some magic. We actually looked at under the hood and the interconnections, and we ended up with a different convex problem, but one that we could solve. So turns out that you can extend this to polynomial optimization. I mean, it's the same deal. You look at the correlative sparsity graph, same idea. You have one node per variable. You have a edge if the variables appear in the same constraint, or if they have cross terms in the objective, and you decompose your polynomial optimization problem along clicks. So instead of dealing with huge polynomials with lots of variables, you can have a collection of smaller polynomials with smaller variables. And this is sort of what's under the sort of sparse Putinar positive Stellensatz or sparse optimization. Okay. Let me bring things a little bit down to earth. I mean, So let me give you an example. Coming from control, one example could be, I give you data that comes from a switch ARX model, and you're actually trying to identify your data, okay? This is a special case of, let's say, semi-algebraic clustering. When you have data that comes from a collection of algebraic varieties, and what you're trying to do here is you're trying to segment the data, okay? And this is, for instance, a very well-known problem in machine learning or in computer vision. So let me start with a very simple version. I give you points, and I say, put points into planes, okay? So baby version of subspace clustering. If you can solve this, you can solve all the other problems. Why is this problem hard? Problem is hard because you don't know your hyperplanes and you don't know your labels. If you knew which points were blue, which points were yellow, all you need to do is least squares fitting. If I knew the planes, I can assign labels by just computing the distance. But the problem is like chicken and egg. I don't know neither the labels nor the parameters of the hyperplane, okay? How do we solve this? I mean, this is a classical problem in computer vision. You can solve it using something called GPCA. And there were all sorts of other ways of solving this, sparse subspace clustering, low rank representations. All of them have horrible scaling properties. So I want to look into what's the intrinsic complexity of this, okay? So I'm going to start by reformulating this as a QCQP. And the way I reformulated this as a QCQP, I throw in a bunch of indicator variables. So for a given point, I have two variables, yellow and blue. Yellow, it's 1 if the point belongs to a yellow subspace, 0 otherwise. Blue, it's 1 if it belongs to a blue space, okay? Now, once I put in those indicator variables, then the two equations have to be true, which means the product has to be true. So, and of course, I need to impose that my variables are binary. So you go through a little bit of work, and at the end of the day, you get something like this. I mean, the first equation says that if Sij equals 1, Xi, it's inlier to Sj. The second equation imposes that your variables are indeed binary. The third equation says I have to assign each point to one and only one subspace, and so on and so forth, right? And if you look at this and you've taken Nechmi's class or maybe Peter's class, you recognize that this is sum of squares. You can solve this using sum of squares or moments. So today, Pete was telling me that he wrote an SOS solver, right? So you try to feed this to an SOS solver, you try to convert this into an SDP, and guess what happens? You die a horrible death. And the reason you die a horrible death is that computational complexity kills you. I mean, anyone that has actually worked with sum of squares type of relaxations knows this. And in here, very roughly speaking, complexity scales as number of data points you have times the number of subspaces power 6. So you're talking about like 2 planes, 100 points in R3, we're talking about 10 to the 8, all right? Now, you go to try to publish this in a machine learning conference or talk to your machine learning colleagues, they will laugh you out of the room because they actually can solve problems like this. Right? When it becomes interesting is when you look at the underlying correlative sparsity graph, because the underlying correlative sparsity graph has a very definite structure. You have each click, you have the parameters of the model or the parameters that determine your subspace and only one of the indicator variables. So if you do a click decomposition, immediately the complexity of your problem pops up. Turns out that if you do click decompositions, you can get algorithms that scale linearly with the number of data points. And what kills you here is the dimension of a hyperplane, or if you're doing an identification problem, the rest of your model. Okay, so the true scaling of your problem in here should be linear in the number of points, and we expect that it will scale badly with the dimension of your subspace. So using this click decomposition, you can get a subspace clustering algorithm that scales linearly with the number of data points. And I don't know of any other algorithm that does that, okay? Which seems really nice. Actually, I'll tell you later why this doesn't work, but in principle, it looks really nice, okay? So what's the moral in here? The moral in here is that the computational complexity of control problems is related to the order of your model. And that's actually correlated what I teach my students, or all of us teach our students. Look for low order models. Not only because the order of the model gets reflected in the complexity of your controller, but also because when you have low order models, the computational complexity of sysid and the computational complexity of control design are much lower. Typically, computational complexity of control problems will scale badly with the order of your system. Okay? So low order models. It's better to have a low order model and then have robust control try to eat the fitting error than try to have very high order model that you cannot identify anyway. Okay. So the next question is this a fluke? I mean, did I pick just the right example to try to convince you? Turns out, not really, actually. Anyway, I just wanted to show you in here that the computational complexity, if you do this, goes for this example from 10 to the 8 to 10 to the 4th. I'll come back to that example later. But if you look at other type of examples, turns out that if you're trying to do model invalidation of switch systems, exactly the same structure pops up. The size of the click related to the size of the order of your model. It's order of your model plus 1. So you can do model invalidation that scale linearly in the number of data points if you do the right corridor or click decomposition. If you try to do data-driven control of switch systems, I give you data that was generated by a switch system, and I ask you to design a controller that actually is guaranteed to stabilize your system. And of course, you want to skip the sysid problem. Turns out that the sparsity graph looks like that. There's one node that connects everything that's related to a common Lyapunov function. And then each one of the leaves in there, they have to do with the complexity of stabilizing a single system, which again is related to the order of your system. So turns out that if you do the right thing, you can stabilize, do data-driven stabilization of switch systems in such a way that the complexity scales linearly with the number of systems you have. Whatever complexity you have for the design of a single system, you multiply that times the number of systems you have, and there you go. Okay? And then another one, I was talking to some of the junior students, doing Koopman operators. When you're trying to learn Koopman operators from data, you can write that as an SDP, and you have the same complexity. It turns out that the complexity in here, now you will have two clicks. One click that's related to temporal evolution, and another click that's related to temporal or spatial neighbors when you're doing the embedding. And then the size of the click is the sum of the two. And so again, that helps you quite a bit when you're trying to learn Koopman operators. We can actually do some non-control applications that we've done. One of them is recovering 3D data, structure from 2D data. And the other one is a very recent paper that we had at the last European Computer Vision Conference, where we're trying to do motion segmentation. You have an image, you have many objects moving, and you're trying to determine how many moving objects I have and assign points to each object. Okay? Turns out that you do some magic, you can put that as a semi-algebraic clustering, and we can do this with only two views. We didn't use an SAP, we used something else related to Christoffel polynomials, but just using the underlying structure, we could actually get something that's 1,000 times faster as a state of the art with the same performance. And we got a reviewer really upset at us. You can see that's a review we got. Apparently, we didn't scrape and bow sufficiently to neural nets, so the reviewer almost killed our paper just because we had a shallow method that was 10,000 times better than the state of the art. And we didn't training. And the guy says, you don't show proper respect to neural nets. So anyway, if you're if you're a control person and you're submitting to machine learning conference, be prepared to get reviews like that. That make no sense. I've gotten reviews where I almost got a paper rejected because a reviewer said, we were claiming convexity, and the reviewer said, functions of one variable can be convex, sets can be convex, functions to variables cannot be convex. And the reviewer rated herself or himself as high expert, so I give up. But anyway, rant mode off. at some point you just look at this and you laugh. Okay, so I mean, what is big data? Now I can start to answer this. Turns out that big data doesn't have to do with the size. I mean, Google size things can be small data, hundreds of points could be big data. And this is trying to capture that. I mean, if you don't have correlations, then that's an easy problem. If you have correlations, and I mean, this is trying to be captured that in a Hankel matrix because you have this Hankel structure, then that's a hard problem. Okay? So computational complexity is related to how data is interconnected or the size of the clicks in the underlying graph. Okay, so you can actually put some teeth into that. So what's a hard problem? What's an easy problem? Look at the underlying graph. If you have large clicks, you're in trouble. If you have small clicks, then you're in good shape. And I think that's much better dichotomy that's just simply convex or non-convex. Okay. All right. So to get people into a room, I was afraid that no one will come to hear a talk from old control guy about optimization. I said, okay, let's throw in some machine learning stuff, right? So I'm just going to show you all sorts of neat things that you can do using control to solve machine learning problems, okay? And it has to do with what's in the relationship between information, sparsity, and dynamics, okay? So suppose that I show you this, and I ask you, can you tell what's going on? And this is an image. The image processing wasn't done by me. It was done by a really good computer vision person, Professor Octavia Camps at Northeastern. If I show you this, how many people can tell me what's going on? It's really hard, right? What if I show you this? How many people can tell me what's going on? So what's going on in here? Dynamics carry information. Your eyes are integrating over time, and they are sort of looking for low order correlations, things that are white noise or noise in there, high order. You'll try to filter that. You're following the dogs in there that have an underlying low order dynamics. Okay, so the first time I heard about compressive sensing, where you can actually get above the Nyquist limit, I thought that cannot possibly be right. I mean, how can we avoid the Nyquist limit? And the answer is because you have a very strong prior. You know that the signal you're trying to recover happens to be sparse in a given basis. So you can take an analogy there and say, well, if I'm trying to recover information, let's assume that actionable or useful information is actually being generated by a low order system. And the way you extract the information is minimize the rank of the underlying dynamical system in some way. Okay? So here's one example. This was also a paper that we published in one of the computer vision conferences. Suppose that I give you a video clip, and then I shuffle the frames. And I ask you, can you unshuffle them? That's what we call bitemporal puzzles. And it looks like I made that problem, but it actually has some interesting applications. Okay? So the idea is that look for a permutation matrix such that the underlying dynamics have low order. And in this case, I mean, we try to represent our video sequence as D, which is a dictionary times a vector of coefficients. And the dictionary we're picking here is actually the Vandermonde matrix of poles. So the number of columns in your dictionary is actually a complexity of your dynamics. Once you do that, if you want low order dynamics, all you need to do is make sure that the vector of coefficients is sparse, because that means that you're picking smaller number of poles for your representation. So I can do things like this. I mean, the one on the left is something that we shuffle. The one on the right is the unshuffled one. So it's an interesting control problem. We actually managed to do things like this. So by using very simple concepts from control theory, you can actually solve things that are non-trivial machine learning type problems. Okay? Which brings me to a question of how do you represent dynamic data? Okay, and I apologize. I mean, a lot of people in here, if they have a background in control, will know what I'm talking about. But the main idea is that suppose that I give you that sequence. You can do what people will do in machine learning, which is take, or in computer vision, take the coordinates of the people in each frame, put it side by side, and that's what's called the data matrix. And then try to do things using the data matrix. But if I show you this, right, this is obviously wrong. But the rank of the data matrix didn't change, which means that working with the data matrix or working with the rank of the data matrix is not the right tool because it doesn't capture what you're trying to capture. So instead of doing this, what I'm going to do is I'm going to Hankelize things. So you put things in a column, then you displace it a little bit, and so on and so forth. And what we all know is that the rank of the Hankel matrix measures the complexity of your system, and it's not invariant under reordering. And all the data that could have generated, all the models that could have generated data you're seeing live in the null space of your Hankel matrix. Okay, all right. We know that, that's this idea. How can we use this for control? And here's an interesting computer vision problem. A lot of tracking algorithms now are called do tracking by detection. So you detect objects in each frame and you try to stitch them together, right? What happens in here? I mean, we pick an example where the object do not have features, or when we're tracking the heads, all of them kind of look the same, right? So what we did is we stitch the trajectories in such a way that you minimize the rank of the underlying Hankel. That's the right assignment. And then we can do things like this. We can actually keep identity labels, even though you have occlusion, or we can actually segment things. And simple application of, again, ideas from systems theory. Okay? Here's another example. I give you elements. I give you trajectories, say from skeletons, from different activities, and I ask you to group things that came from the same activity, right? And you know, what we decided to do here is we needed to sort of compute a distance between time series, right? How do you compute distance between time series? Because the time series, they have different initial conditions, maybe don't line up. So what we decided is, okay, we're going to embed this data in a Riemannian manifold and use a manifold distance. Okay? So what is the Riemannian manifold? Well, we know that somehow the Hankel matrix should be involved, but it's hard to embed a Hankel matrix and Riemannian manifold because they are not positive definite. So what we did is actually we worked with a Gram matrix, HH transpose, that's positive semi-definite. We embedded that in the positive semi-definite manifold, and we use a manifold distance. And it actually, once you use a manifold distance instead of Cordo, doesn't matter when we use. This is a paper that we had a few years ago. We could beat quite a bit the state of the art. And again, this is a shallow method. Just Hankelize, compute the Gram matrix, and do manifold distance. We use a JBLD, but you can use a KL divergence or the affine invariant rate. And we were, again, we got really good. It was an interesting conversation with the reviewers. Trying to explain what Hankel matrices and Gram matrices are, but the paper got in. So one of the things I learned, I work with a computer vision person. She's my filter. Because the way I write my papers, they're written for your control audience, and bam, every single time they bounce. And if you run that, if you're working with someone, or if you're trying targeting a community that's not your own community, better work with someone from that community and try to find out how to write things. First, don't be condescending. Secondly, write things explained in the way that people in that community relate to. Okay. So here's one more example. Suppose that I give you that video and I ask you, can you tell me who's in the same team who reacts to whom? Turns out that you can solve this using something called Granger causality. Okay, so you have something where each time series becomes a node in a graph, and you say that, say, green depends causally on the other ones. If I can write green as a linear combination of perhaps delayed versions of my thing. So at the end of the day, what you need to do is you need to identify what we call dynamical graphical model, where each node is actually a time series, and each of the edges is a filter, and what you need to do is you need to sparsify this. Okay, you can write that this is an SCP. We actually solved this using Frank Wolf that ended up being a lot more efficient, but I can do things like this. I mean, you give me a video clip and actually you can analyze the video clip. And there was no semantic analysis in here whatsoever. I mean, those relationships came out entirely out of analyzing time series and trying to find a filter. So it's pretty neat. So the message here, if you're a control person, there are lots of interesting problems out there where there are hidden sysid type problems where you just look at the dynamical system that's underlying your system, and that's the key to encapsulate your dynamics. Okay, don't compare time series, compare the underlying system, right? And sometimes, and many times, you can actually do that without actually finding the system. Just take two Hankel matrices, put them side by side, and see if the rank goes up or not. The rank doesn't go up, they are the same system. The rank goes up, they are different. As simple as that, and you don't have to sort of slide time series and whatnot. Okay, so I have a few minutes left. So let me show you why I was cheating. Let me go back to semi-algebraic clustering, the one where I was saying, look, we can have this algorithm that no one else has that scales linearly with a number of points. We're great, except that we're here. Yeah, way out there, we scale linearly with a number of data points. The overhead and the computational complexity kills us long before we can actually get to a point where we start gaining things, right? So the problem in here is that you have to deal with very large semi-definite programs. And dealing with large semi-definite programs is what kills you. So just bear with me for 5 minutes. I'm going to tell you a few things that we're doing in my lab to how to deal with very large semi-definite programs. And so everyone is on the same page. What's a semi-definite program? You're trying to minimize and linear cost over the intersection of the positive semi-definite cone and an affine subspace that's called spectrahedron. Typically, the most efficient way to solve this is called interior point method. So you throw away the positive semi-definite constraint, you replace that by a penalty, typically log det, and you put a weight function, 1 over t. So you start with t very small, and you let t go to infinity. And you ask me, why don't you just put a huge t, do it in one shot? And the answer is because you get a very stiff optimization problem that you cannot solve. So as you change t, your solution traces something that's called the central path of the optimization. The good thing about this is that this is extremely efficient. You can show that you find the solution in 40, 50 iterations. The bad news is that each iteration is horribly, horribly, horribly expensive because you have to compute the Hessian, you have to store the Hessian, and that's what kills you when you're trying to do semi-definite program. Okay, so one idea that Amirali Amadi came up with, working with Paulo Parrillo, is don't work with positive semi-definite cone. Work with simpler cones, a cone of diagonally dominant or scale diagonally dominant matrices. Okay? Without going into many technical details, when you work with the cone of diagonally dominant matrices, you get linear programs. If you use scale diagonally dominant, you get second order cone programs. Okay, so the good thing about this is that when you work with much simpler cones, you get things that work much faster and you can solve large problems. The bad news about this is that typically they are suboptimal and you get stuck far from the optimum. Okay, so the approach that we're taking is move until you hit the boundary and then do what we call a centering step. Move away from the boundary for as much as you can. Okay, and the centering step involves maximize the condition of your present solution subject to a condition that, or the constraint that you don't increase the cost. So you're moving normal to the surface. Okay, that's a great idea, except that solving this problem, it's every bit as difficult as the problem you started with. So you don't gain anything. So what we did is actually, we replaced the positive semi-definite matrix in there by, again, diagonally dominant or scale diagonally dominant, put the penalty function, and I mean, I apologize, this is kind of rushed because I'm running out of time. I'll be happy to talk to you offline about this. But the main result in here is that when you do this trick, by the time you're done, you're back to the central path of the optimization. So you can do things like this where you decrease doing second order programs or LPs, center doing second order programs or LPs, go like this, and you actually, that's an upper bound on the number of iterations you have to do for this to converge. So it's extremely efficient. And here you have one example where you can see the behavior. You see it goes down, that's the sort of optimizing phase, plateaus, that's when we're centering, goes down. But doing this, I was able to solve very large semi-definite programs in a laptop. So, okay, so just to wrap up, how about doing control now? Okay. Now, if you see, I open up the box and I tell you all the wonderful things that we did in the theorem. And we have this huge amount of theory behind that. We're talking about equiparametrization, interpolation, Hahn-Banach separation hyperplanes, IQCs, blah, blah, blah. All of that is transparent to you now, right? You get a semi-definite program and you solve, but the theory is still ahead of the computational tools that we have, okay? We still don't know how to efficiently solve lots of the problems that we get. So maybe we can use sparsity to provide a way out, or maybe we should not deal with SDPs. Maybe we should do gradient search, and some of the research in control now is saying, look, forget about it, don't do SDPs or anything else. Or, this is me clutching my pearls. I mean, a heretic. Maybe we should look into something different. I don't like it, but not that we use a neural net, train a neural net, but we use the fact that they have GPUs and they know how to do gradient search in a good way and you exploit the architecture. I mean, go to the dark side, but only slightly. So whatever that means. Anyway, that's all I have to say. Many thanks to the control group for coming here, except Najmiya, because she's making me work really hard. And anyway, I'll be happy to answer questions now or offline. Peter, is there? Yeah. Is there? Can we see the chat? Or
I am.
Okay. Yeah. Well.
So how would you explain how at the beginning you said that these machine learning people can solve 10 to the 8th order problems when for us a big problem could be
size of the click? You can solve 10. It all depends on the problem you're trying to solve. If you're trying to do classification is one thing. They cannot solve an identification problem with 10,000. So it's all in the type of problems you're trying to solve. So it turns out that control people have to solve some problems that involve temporal dependencies that perhaps machine learning don't have to.
So machine learning just tends to more often have these lower click problems.
Yeah. Yeah. Yeah.
When you were talking about the correlated decomposition, I was surprised that like spectral decomposition or like single values didn't really come into the picture. Is that because there are like certain limits?
Say it again. Sorry, couldn't.
So when you were talking about portal decomposition,
yeah,
it was kind of surprising to me that like singular values or like spectral decomposition did not become like part of that conversation. Is there like a particular reason? Like there's
I mean, I don't know how to relate SVDs to computational complexity. I mean, there are other things. I didn't talk about symmetry or everything else. SVD come from a different thing, because when you try to do this, sometimes you run into horrible conditioning problems, and then you have to do that. Or you're trying to do rank minimization because you're trying to force things to converge to a rank 1 solution, and then you try to minimize the nuclear norm. But as far as I know, computational complexity, it's not related to spectral properties. Yeah.
So you, I mean, you heard of the click dimension as being the critical link. So is what's happening when you solve most control problems, like there's Lyapunov conditions or dissipation inequality. So you get a stored matrix at the center of the matrix inequality, and that's suddenly like blowing up the click dimension?
Yeah, because it relates, I mean, unless you have some sort of sparsity, let's say that you have agents and then you can do diagonal things. Otherwise, everything is related to everything, and that's where you die. But when I was doing the switch systems, I was using a common Lyapunov function, and that's why I got the chordal sparsity.
maybe related to that point, like Granger has this results showing that for monotone systems, you can get around it like quadratic length of functions that are diagonal.
Yeah.
So you get sparsity where your click dimension becomes one all of a sudden.
Yeah. Right, guys, it's Friday. Thanks for staying until the end. I mean, I know it takes, anyway.
Our speaker again.
Okay. Hopefully before you're headed to do
Yeah.
Speaking of the sparsity of the like a video or like a dynamic system,
Yeah.
sparsity. I just kind of related to like when we were solving like CFD problem.
Okay.
It's also a sparsity matrix.
Yeah.
We also use CFD dynamics. Yeah.
I mean, when we're doing chordal decompositions, on top of looking at time, we also look at symmetries. And so I'm not an expert in CFD, but I'm sure that maybe it can be helped.
And I like to write it because like CFD, if you write the solver in the matrix,
Yeah.
it's more like a
Okay. So I mean, but have the matrix in the sparse form, and you're trying to find a Lyapunov matrix. The clicks. Structure. I don't think their values come into the picture in terms of complexity.
I tried like finding the website you had on the
I'll start bringing up. Sorry. But I'll send me an email and I can send you the presentation and everything.
sorry.
There's no calculation.
I would like to see the
Are you using it then?
It's not, I don't worry. It's
I tried to find a way to
but it's only one part.
If I'm able to push further, I'm happy to go. Just let me know. You suggested that in Gilmore was it at all?
I did recommend you're very correct.
Yeah.
I'm happy to collaborate.
I didn't want to be found.
I'll ask both clients.
All right. And I have tons of others. Nice.
Okay, thanks.
Yeah. Sometime I'll be there sometime that day. Or you send me an email, I can go later.
Get back, you can just your receipts and I'll reimburse you. So I was.
Are you sure?
I am sure.
Very nice to meet you. Thanks for making the arrangement.
You're welcome.
We haven't met, but maybe.
Oh, okay.
This is what name is.
Thanks for the microphone.
I need to share some of the reviews we have been getting. I mean, one of my favorite reviews that I need to share is that we had a paper that was much better than the state of the art. We get reviews back and say, oh, this is great. This is much better than the state of the art. Too much math. Send it to control conference. And you know the one I showed about QCQP with getting the structure from motion. The first time the paper was rejected because I wrote it as a moment paper. So SOS, a moment laser hierarchy, got rejected. So I took everything out. I put it as a QCQP with a mysterious matrix that was M. Paper, but it's same paper.
Did get it on the Zoom chat.
I was looking at something recently, and then I was looking at a quadratic programming language. Anyway, it doesn't really matter. And I mean, I know that was with the field, and these people like they have a language and they call it deep, and I'm like, there's nothing deep about your language. It's just like call it deep because it's all marketing.
Yeah,
So,
yeah. But
it's
the
not
problem
100% marketing.
is that if you know the language,
Yeah.
then you bounce.
Yeah, for sure.
I mean, and they have certain ways. I mean, you can tell I got really pissed when we have this thing that beats the hell out of the state of the art, and they say, but you didn't use a neural net. We're gonna reject that because you didn't use a neural net. I'm like, okay.
Which conference?
I mean, that was the European Control Conference 2022, ECCB. I mean, the paper got in, but squeaked in.
Here's the question you got in the chat if you want to answer it. Do a relaxation that gives you a lower bound. Why don't you try a restriction as well to get an upper bound? But I guess any sample gives you an upper bound, right?
Any sample gives you an upper bound.
Yeah. Maybe with the restriction, that would just make it. So like the rank relaxation problem, you wouldn't normally do a restriction. Any sample gives you an upper bound,
right?
As long as it's feasible,
right? And then you do some whatever you can, and then at the end, if you really need to do certificates, you try to do a KKT. And I mean, if you have good karma, the KKT says, yeah, you're at an optimum.
Yeah.
I got just real quick question. So I remember you showed the video of the MBA, right?
Yeah.
Yeah. Is there a paper really?
Oh yeah, there are a couple of papers I can send you.
Okay.
I mean, they're all papers, but yeah, we had.
What's the title of that one? Okay.
I mean, I have to find it, but it's in one of the computer vision conference. Oh, yeah. If you email me, I'll promise I'll email you back.
Yeah, yeah. I'm interested in that one.
Okay.
Okay. Thank you so much.
Sure. No, not next me and Charlie. No, I'm pretty embarrassed. I should.